Okay, this is a quick video about RC circuits. I'll go over the theory and then I'll do an example with a twist at the end. One of the things you'll notice whenever you see an RC circuit is there's always switches. And the reason there's switches is because RC circuits are not constant current, they are time dependent circuits. And that means that their behavior changes based on the moment you turn them on. And so we always put a switch to decide when we're going to start this process so that we can watch it evolve over time. When you close the switch, you will allow a current to start to flow through this circuit. The battery will start to send positive charges through the resistor and to the capacitor. Now, bear in mind, where do these charges come from? We're actually pulling positive charges off of the capacitor, and the battery is moving them all the way around the circuit to get to the positive plate. So the battery definitely has to do some work here in order to accomplish this. One other thing to point out is notice I have a Q here, and I say that as the charge flows through the resistor, it has to go to the capacitor. Another way to say that is the rate at which charge accumulates on the capacitor is equal to the current. The rate, dq dt, at which charge accumulates is equal to the current. So we'll want to make use of that when we do some real math. Before we do some math, let's make some guesses, though, some wild guesses. At first, the capacitor is empty. We know that because it hasn't had any time for charge to get there. But if the capacitor is empty, that means that the voltage on the capacitor is zero. That means all of the voltage has to be across this resistor. And if all of the voltage is across the resistor, the amount of current that flows, it's as if the capacitor wasn't there. So we say empty capacitor behaves like a wire or a short. A short is just a branch of a circuit that offers no resistance to current. It's as if it were just a wire. Okay, what about in the long term? In the long term, eventually this capacitor is going to get full. What do we mean by full? We mean that as more charge piles up on this capacitor, it's going to create an electric field that opposes the current. Eventually, that electric field is going to be so big that it kills the current and the circuit will have stopped. At that point, the voltage across the capacitor has to be the voltage across the battery, and the voltage across the resistor has to be zero. In other words, what we're saying is the current will go to zero and the capacitor will be full. Since there's no current, the capacitor behaves like an open switch. In other words, it simply refuses to allow current to flow down the circuit. If we wanted to graph these things, so versus time, we might guess that at first it's very easy to load up the capacitor because there's no charge yet. But as we add more and more charge to the capacitor, it loads slower and slower because it requires more effort to oppose that electric field. Another way to say that is at first we expect a big current and then later on we expect a small current. And since there's a small current, we're going to load charge slower at the end than we do at the beginning. Okay, enough guessing. Let's do it for real. We'll make a Kirchhoff loop, and we'll make the loop for any random time t, not after a split second and not after infinity. Let's make use of the fact that we said that the current was dq dt. Let's rearrange a little bit, and what we end up with is a differential equation. Now, this isn't a super hard differential equation. It's a separable differential equation. So that means that we can put everything involving q, so here are my q's, on one side and everything involving t on the other. You actually may have seen something like this when you did drag. You end up with almost the exact same thing when you look at a ball falling through the sky. In any event, this equation I wrote is true for any time t that has a charge q in it. So if it's true for each time, I can add up the small amounts of charge that are moving at each time, and that means that I can integrate both sides and it'll still be true. So if I integrate the left, I end up with some logarithm, right? If you're puzzled about where the denominator here comes from, bear in mind that I have two limits. I'm going from 0 to q. And okay, when you plug in q equals 0, you don't get 0. There's something left, e over r. So you really get a log of one thing minus the log of another thing. And I fractionized it to make it easier, okay? This side's easy. You just end up with a t. So if we unlogify it, in other words, we exponentiate and we do a little bit of algebra, you end up with something like looks like that, and then one more piece of algebra, and we finally have q as a function of time. Okay, so this will tell us at any instant how much charge is on that capacitor. If we want to know the current, no problem. We just differentiate, and if we differentiate, we end up with something that looks like that. So all of our math has told us that. Is that consistent with what we guessed? Well, let's see. We said that q of 0 should equal 0. Well, if I plug in t equals 0, then this term is a 1. If that's a 1, then this is 1 minus 1 or 0. So this checks. At infinity, if I plug in t equals infinity, then this last term is a 0, and then I just end up with this. So this also checks. Meanwhile, for the current, if I plug in 0, that's just a 1, so that checks. And if I plug in infinity, I get 0. So this checks. And if you plot these two functions, you get the exact same graphs I drew before, because of course I cheated and I actually plugged those two equations in right from the get-go. This just confirms, though, and this is something to keep in mind when you do problems, an empty capacitor behaves like a short. A full capacitor behaves like an open switch. We're going to make use of that in our example problem later. Okay, I want to talk about the time constant of the circuit. So this gives you a sense of how long this process takes to happen. So the time constant is RC, and if we do a little quick calculation, after one time constant, we get about 63% of the total charge we're going to have, and the current drops to about 37% of the total current that we had. So look, if you have a large capacitor, it can hold a lot of charge. That means it takes longer to charge. If you have a big resistor, it means that the current has to go slowly. That means it takes longer to charge. If you want to look at this, you can say that a small time constant means that you charge very quickly. Look, this is almost at maximum, almost immediately. A small time constant means you charge slower. So this could mean 1 microsecond or 4 hours, depending upon the values of R and C you choose. It's up to you. If you want it to load fast, make the time constant small. Okay, the last thing I want to talk about for this case is energy. Okay, so we know that a capacitor has an energy Q squared over 2C, and we know that in the long term, the total voltage on the capacitor will be this. And so the Q max is CE, and so if you do the math, you end up with that much energy on the capacitor. Now, who puts the energy on the capacitor? The battery puts the energy on the capacitor. We said that the battery has to do different amounts of work depending upon how much voltage difference there is on the capacitor. In other words, as the capacitor loads, there's a smaller voltage difference to consider. And so that's why we have to look at moment to moment how much power the battery is putting out. And if we integrate that, that'll tell us the total energy put out by the battery. So if we do this calculation, we actually end up with twice as much energy as went to the capacitor. We are missing half of it. And if you say, well, where did it go? Of course, resistors dissipate energy for a living, so it must have gone there. Let's just make sure it did. Let's integrate the power across the resistor, so that's I squared R. This one I'll actually do for you since it's a little squarier. So if we do that, you punch it in, now you get the other half. In other words, we're missing half because the resistor takes half. And notice, this doesn't depend on the resistance. Big resistor, small resistor, we lose half no matter what. So you'd think maybe if we have less resistance, less energy loss. Wrong. Okay, what does this say? This says that the energy of the battery has to be split between the capacitor and the resistor. And we know that eventually, at t equals infinity, equal amounts are spent on both. I'm no engineer, but 50% waste doesn't sound very good to me. The other thing I want to examine really quickly is it the case that moment to moment, it's giving the same amount of energy to each? So let's look at how much energy is spent on each over one time constant. So over one time constant, we end up with this for each of them. I'm just plugging and chugging here. So notice my integral now goes to tau, only one time constant instead. And what we actually see is after one time constant, only 40% of the capacitor energy is there, but we've already burned 86% of the resistor. So in other words, the resistor is getting its energy early and the capacitor is getting its energy later. I'll put this here for now because I want to compare it when we do our example problem later. But after one time constant, only a third of the energy that the battery has put out has gone to the capacitor. Eventually, the capacitor will get 50% of it, but for now, it's only getting 33% of it. So the capacitor is less efficient the less time you let it charge. You lose more of a fraction of your energy. Okay, so Early on, the energy goes to the resistor. Later, it goes to the capacitor. You might say, well, actually, I know how to solve this. There's no problem at all. I'll just keep one resistor and make 3 capacitors. This is not going to work. This is not going to work because now you have 3 capacitors. And what that means is you need 3 times as much current in order to feed it. You're still going to burn through your capacitor, through your energy. Another way to see this is, look, these 3 capacitors can just be reduced to a CEQ, and then the math is exactly the same. You're going to burn through 1/2 CEQ V squared, so that doesn't fix it. There actually is a way to fix it, and that is by using an inductor and a diode. I am definitely not going to tackle this in this video. I promise I'll do it in another video, but I'll just say very briefly, the reason why the inductor is able to increase energy efficiency is it throttles the voltage. In other words, we said before that the most current flowed when there was the biggest voltage difference between the battery and the capacitor. You got a huge current in that case. As the capacitor filled, the voltage difference between the capacitor and the battery was less, and so as a result, you wasted less energy with a big current. The inductor's job is to throttle the voltage so that we build up slowly rather than quickly. You'll have to take my word for it, and I'll do it in another video. The reason I have this guy called a diode is that the diode only allows current to go in one direction. And while I won't prove it to you, what I'll say is that when you put an inductor and a capacitor together, the current becomes sinusoidal and it sloshes around. And I want to prevent it from sloshing around. I only want to be able to charge the capacitor and then have it locked there. We'll go over that in another video. Okay, now if I open the switch, I actually change nothing. The capacitor is still charged. It can't discharge because there's no circuit through which it can charge. The switch simply does not allow current to go. So if I want to discharge this, what I do is I build a separate branch on the other side with another switch, and then I close that switch. Once I close that switch, the capacitor will start to get rid of its charge as fast as it can. The positive charges want to be reunited with their negative charge brothers on the other side. As those charges go through the resistor, as they leave the capacitor, they must go through the resistor and they'll burn up all the energy that they had doing it. Eventually, we expect this circuit to be dead as the resistor steals all the energy. Now, notice what I said. The rate at which the charge leaves the capacitor is equal to the current, and that's why I have a minus sign here this time. And so that's the big difference between a charging and a discharging circuit. Okay, let's do the math. It's a Kirchhoff loop again. This time the Kirchhoff loop is cleaner because there's no battery, so the algebra is cleaner, which is nice. Notice I plug in a minus dq dt. That turns that guy into a plus. One more step of algebra. I'm at my separable differential equation again. And if I integrate just like I did last time, I can eventually end up with this. Now notice, we don't go from 0 to q. We're not starting with 0 charge. We're starting with q naught's worth of charge. What's q naught? Well, remember, this is charged to E, and so the original charge is CE. If we want the current, all we have to do is differentiate. And so there we go. You differentiate, and now you have your current. So how does this square? We have 2 new equations. The current looks basically the same as it did last time, but now the charge is also a decaying exponential. Of course, the charge has to decrease. Let's talk energy for this circuit too. The capacitor starts with the energy it began with after it was charged, so that's 1/2 CE squared, and eventually it should have nothing. So I'm not going to do any integrals this time. I'm just going to assert that all of that energy had to go to the resistor. Where else could it go? I do want to talk about how fast, though. Like, how fast does the energy leave? And I want to bring the time constant back into this. So let's see how much energy gets dissipated by this resistor in one time constant. So if we plug in and we do I squared R and we integrate to RC, which, as you recall, is the time constant, you end up with about 86% of the energy lost in the first time constant. So the energy gets crushed fast. And the reason it gets fast is because the resistors are using the bulk of their energy early on. Okay, so this is our summary so far, and then we'll do an example. When you charge, the charge increases over time and the current dies off exponentially. When you discharge, they both die off exponentially. And this is important. An empty capacitor behaves like a short. It's as if it was just a wire and it isn't there. A full capacitor allows no current. It is an open switch. The energy from the battery eventually gets evenly shared between the capacitor and the resistor. You lose all that energy, but it doesn't depend on the resistance. Okay, so here we have a legit problem. This is a problem with two switches and two capacitors. And what I'm going to do here, this is the twist. In before, I had one switch open at a time. I'm going to go ahead and I'm going to close both switches on this one. And let's see what happens. Now, one thing I want to point out is that when I look at this circuit, I see this and it drives me bananas. I go, this is so wasteful. This is going to make it so complicated. Let's reduce it. Let's just take the equivalent capacitance and get that out of the way right away. So I do that. The numbers for the capacitors over here, one is 1, the other is 2, so I end up with a 3 farad capacitor. Okay, and let's get to work. It says let's find the current in R1 and R2 immediately after the switch is closed. Okay, so at t equals 0, C12 acts like a short. In other words, it's as if it isn't there. That means that all of the current is going to go through this. Okay. Another way to say that is, look, there's no charge on the capacitor when you first turn it on. That means there's no voltage on the capacitor when you first turn it on. That means this guy's not allowed any voltage either. That means he's not allowed any current. Either way you slice it, I2 equals 0 at first, and IC and I1 have to be the same number, and that number in this case is 1 amp. Okie doke. So after a long time at t equals infinity, C12 acts like an open switch. That means that IC is going to be 0, and then the current that flows through I1 and I2 is the same, depends on the total resistance, and you end up with a third of an amp. Okay, how about the charge? Now, after a long time, C12 is in parallel with R2. In fact, not even after a long time. I would just say always C12 is in parallel with R2. However, I know exactly how much voltage is on it after a long time, because after a long time, I know the current going to R2. And so whatever the voltage across R2 is, that's the same as the voltage across the capacitor. And if you want charge, you just multiply capacitance by charge. So that's how much charge is on each, and that's the total amount of charge. The total energy on the capacitor, you can get one of two ways. You could say that it's Q total squared over 2C, or you could say it's 1/2 CV squared, now that we know it's voltage. Either way, you get 200 over 3 joules total. Okay, now let's do the hard part of the problem. This is where the twist comes in. Now, I've said what the total energy is going to be on the capacitor, but now it says find the current from the battery as a function of time. I want to explain that this is not quite so simple as it was before. I used to say that any of the charges that flowed through the battery used to have to go to the capacitor. That is definitely not true anymore. Some of the charges go there and some of the charges go there. Another way to say that more cleanly is that my current splits. Some of the current goes to IC and some of it goes to I2. What we have to do is write a current conservation equation. So I have I1 equals IC plus I2. And then in this case, I can still do this dq dt business, but that is only about IC. It's not about any of the other currents in the problem. And so what I've done is I've solved for dq dt. How do I get rid of these other variables? Well, I need Kirchhoff loops. So I'm going to make one loop on each side. And on the right side, it's an easy loop because the voltage across R2 has to be the same as the voltage across the capacitor. And then in this loop, you have three things. What I've done in both cases, you can pause if you want and check my algebra, make sure I didn't do anything illegal or foolish. I've solved for the current in both those cases. Okay, and so the plan is to plug those items in to dq dt and create a differential equation that looks like the differential equations that we had before. If I clean it up a little bit, I have this as my equation. Now, admittedly, this is a little ugly, and so I'm going to clean it up by introducing a constant. And the constant I'm going to introduce is called tau, because that is exactly what this thing is. It's the time constant. If I insert that, this thing looks a lot neater. It looks a lot like what I had before, except I used to put an RC there. Now there's a tau instead. I could have used tau when I did this in the first case, but I wanted you to see the RCs. I'm just showing you that we're on familiar ground. This looks very similar to what we did earlier, so I'm just going to blow through this algebra and end up with my equation that now is legit and good for the charge on the capacitor as a function of time. So now it works the same as it did before, but my time constant is a little different. Let's plug in some numbers. So this looks like 20 times 1 minus e to the minus t over 20. And one thing to note immediately is that eventually there will be 20 coulombs worth of charge on this parallel plate capacitor, which is exactly what we predicted in the first place. So that's our sanity check, right? Okay, now let's find I1. So just to be clear, this is my loop from earlier. I had Q and I in terms of each other. So I'm taking my Q and I'm solving for it. And I end up with this as my final result. Okay, so one thing to bear in mind is that when T is 0, this is 1 amp, which is exactly what we said. When T is infinity, this is 1/3 of an amp, which is exactly what we said it should be. So this is also good news. Okay, here's the problem. The problem is if I integrate this over time, I'm going to end up with infinity because I have this constant term here. And of course, I'm going to end up with infinity. The battery sends current forever. So this definitely doesn't fix my efficiency problem. It might be cool to see, though, in the first time constant, maybe somehow this makes it better or worse. Let's look at what happens in the first time constant. This I can actually integrate. So I know the current that the battery produces is a function of time, and I know the battery's voltage. So that's just multiplying 10 times the current that I figured out up here. If I do that, I end up with about 151 joules. What does that mean? Well, let's find out how much is on the capacitor after one time constant. If I do that, I end up with about 26.63 joules. That is about 1/6 of the energy the battery has put out has ended up on the capacitor. If you recall, we definitely did better than this last time. When I was just charging it with one resistor, after one time constant, 1/3 of the energy that my battery had put out had gone through to the capacitor. And so this is definitely not a solution either. In fact, as you probably would guess, adding another resistor and giving charge places to go makes the problem even worse. Okay, anyway, we covered most of the cases that you'll see in an RC circuit. I hope this video was more helpful than confusing.